So when we left our hero last time, we were struggling with this, we're sort of halfway through our journey of saying, okay, we've pipelined the processor. Remember, we drew stripes across the fish. And now we're sort of trying to make sure it's still a fish. In our case, we're trying to make sure we can still execute programs correctly. And we talked about the problem of making the branch decision in the RF stage meant that the instruction that was already noodling its way through the stage before, the instruction fetch stage, the IF stage, was already in the pipeline, and so we had to sort of annul it. We chose to, by default, annul an instruction when the branch was taken, because we didn't want to execute the instruction. That was the instruction following the branch, which only happens when we don't take the branch. And then we moved on. We're currently looking at a 4-stage pipeline, although quickly today it will become a 5-stage pipeline. But we have a 4-stage pipeline, and we're noticing that this set of instructions here, where we are producing a result in one instruction, in this case the add is producing its result in R3, is being used as one of the operands in the subsequent instruction. And so if we think about this a little bit, because of the way the pipeline works, the add actually writes its answer into the register file at the end of cycle I+3. And that means that starting in cycle I+4 and beyond is when the updated contents of R3, the new contents that were updated by the result of the execution of the add instruction, okay, are available in I+4 and after that, and subsequent cycles. And so that was fine, except that we have this poor compare in cycle I+2 in the register file stage. And the job of the register file stage is to go fetch the operands that the compare requires, in this case the contents of R3 and the constant 100. And if we can't look on the register file because it's not going to be there, in fact it's not there in cycle I+2, and in fact it's not even there for all of cycle I+3, it's only at the boundary, the clock edge separating I+3 plus I+4, where the content finally gets written. Okay, so we're sort of going, oh, well, we need to fix that problem. And so the way we chose to fix it was to go off and resolve the problem by noticing that the information that we wanted was actually coming out of the ALU. That add instruction was, when the add instruction is in the ALU stage, the output of the ALU towards the end of that cycle is, in fact, has the actual binary bits. Well, it has the number, the integer that will be written into the R3 register at the end of the next cycle. So we actually have the number we need, it's just not in the register file. And noticing that we actually have the number we need suggested to us that we could modify our data path, that when you wanted to get the contents of a register that was a destination register of an instruction that was ahead of you in the pipeline. In other words, an instruction that came before you in the program, so it's ahead of you in the pipeline. We actually, in this particular case, already will have the information that we need. And in fact, if we could somehow get it from the coming out of the ALU and back into the RF stage towards the end of cycle I+2, we'd be sitting pretty. We'd have what we wanted. And so, in fact, we've introduced this notion of bypassing. We've added an ability for the RF stage to notice when instructions that are ahead of us in the pipeline are producing the result we want. We can actually forward it from those pipe stages that are ahead of us. So from the RF stage point of view, currently the stages that are ahead of us are the ALU stage and the write-back stage. And so we can sort of reach up and say, I'm going to borrow that number. I know it's going to be in R3. I'm going to look. I want the contents of R3 as a result of executing the instructions ahead of me. And that number is there. So we'll simply put some extra multiplexers in our data path to allow us to select that as one of the sources for the contents of a register. So not only can I get the register from the register file, the contents of a register from a register file, I can get it from the output of the ALU, or I can get it in the write-back stage. And after that, of course, it would be in the register file, and I don't need to get it from any other places. Okay, so we could deal all this in software, but we've chosen to go ahead and add that special hardware and do the forwarding. And in fact, if we go off and analyze what's happening here in the diagram, we can see the multiply, which also wants R3, can also get it from the write back stage. Notice it's not quite in the register file yet. It only gets in the register file in I+4. So the multiply is getting the information it needs from an instruction that has preceded it down the pipeline. The compare instruction is actually getting both of its operands from different pipeline stages. And so we have to make sure, of course, that we can bypass for both the contents of the RA register and the contents of either the RB or RC registers, depending on what the value of the RA2 cell mux is. Okay, and here's a sort of a quick and dirty sketch of how we need to modify the actual data path. And what we've done is to put some multiplexers in that allow us to go ahead and instead of taking the output of the register file, to instead also fetch the number we're looking for from either the output of the ALU or perhaps the output of the WD cell mux. So any questions about that? It's just really a way of getting the number we want that we know will be written into the register file. It just hasn't arrived there yet. So it seems like a lot of extra hardware, but the advantage we're getting of that is that perhaps our processor is running 3 or 4 times faster than it had before. So we're trading some extra transistors for hopefully a much speedier execution. Okay, and we're saying, oh, this is great, good. So we're done pretty much, I guess, with bypassing.